So really basic stuff, which is what's organic chemistry? It's the chemistry of like carbon compounds. And so you're going to study molecules that have carbon in them. And just remember that carbon makes 4 bonds, hydrogen makes 1 bond, nitrogen makes 3 bonds, oxygen usually makes 2 bonds. So you should know how the structure of how the structure of an organic molecule looks like. That when you draw an organic molecule, every atom must be making the right number of bonds. Like carbon, any carbon, this carbon over here is making at the moment 4 bonds, right? This carbon is also making 4 bonds. This carbon is also making 4 bonds. The oxygen should be making 2 bonds. So it is. This one is making a double bond. Hydrogen atoms, they make just a single bond. So that is the first thing. And you should know how many types of formulas you've got. You've got a molecular formula, which is that it shows no information about or tells you no information about the structure. It just tells you how many atoms it's got. You've got a fully displayed formula. In fully displayed formulas, you show every single bond. Every single bond is shown. You've got a condensed formula. What happens in a condensed formula is that you don't show all the atoms. What you just condense it. This carbon has three hydrogens. So this is CH3. This carbon has 2 hydrogens. So that's CH2. This carbon is CO and OH, right? So that's the condensed version of this. If you've got a branched molecule, you can condense it. Branches are written in brackets. So the first carbon, that's CH3. The second carbon, that's CH, right? But then it's got a branch over here. So that's a bracket CH3. The next carbon is a C with an H, and then it's got a branch of CH2OH. So this one is a carbon with an H. Plus put this in a bracket, CH2OH. Then the last carbon, that's CH3, right? And you have to, when you write condensed formulas, you have to differentiate between aldehydes and alcohols. An aldehyde would be written as CH3, CHO. An alcohol will be written as CH3, CH2, and OH. So make sure that aldehydes are written as CHO when you condense them, and alcohols are written as OH, right? Is that clear?
Yes, sir.
And you've got skeletal formulas. Skeletal formulas are that when you draw a skeletal formula, what happens is, can you just hold on 1 sec? Give me 1 minute.
Okay.
Sorry. So coming back to this, we've got skeletal formulas. In skeletal formulas, you just show the carbon atoms, but you don't even show the carbon atoms. You just imagine them as dots, and you connect the dots together, not in a straight line, but in a zigzag line. In this one, you've got 1, 2, 3, 4 carbon atoms. That's 1, 2, 3, 4 carbon atoms. And any other thing, any functional group is shown, like you've got double bond OH. So you're going to put double bond O and OH on this carbon atom, the 4th one. On the 3rd one, there's a double bond O. So skeletal formulas are that you just show. So what you do is you just show double carbon. Just 1 second. Sorry. As a skeletal formulas are that you just show carbon bonds, right? So over here you got 1, 2, 3, 4 carbon atoms, right? So 1, 2, 3, 4. Second one, there's another carbon atom. That's from the second one, there's another carbon atom. Third one, there's another carbon atom, right? So it's 1, 2, 3, 4 carbon atoms on the second one, and the third one, there's an extra carbon atom that's coming out as a branch. And you add the functional groups. So on this carbon atom, there's an OH. So I'm going to show an OH next to it. Is that clear?
Yes, sir.
And we can try and draw the skeletal formula of this carboxylic acid. So what would it be? It's going to be, it's just 3 carbon atoms, right? So it's going to be 1 and 2, and then it's 3, right? That's it. So 3 carbon atoms. And I'm going to show the functional group, which is what's the functional group in this thing? So the function,
COI.
so it's going to be double bond O
Yes. And
and
single bond.
OH, right?
Yes.
So that's my skeletal formula for this thing, right? As anyway, so what else? We'll just revise that. Remember counting. How do you name them? It's meth, eth, prop, but, pent, hex, hept, oct, non, dec. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So hept is 7, hex is 6, pent is 5, 4, 3, 2, 1. So in AS you did alkanes, alcohols, carboxylic acids, and aldehydes and ketones as well. So if the molecule is an alkane, that's ane, it's going to be ene if it's an alkene. Ol if it's a alcohol, oic acid if it's a carboxylic acid, al and one, right? Aldehyde is al. So it's going to be pentanol, pentanone, pentanoic acid, pentane, pentene, right? If it's got 5 carbon atoms. So simple straight chain molecules. This one is an aldehyde. Hopefully you know this is an aldehyde. Double bond O. You put a,
Yes, sir.
so that's butanol. It's this AN in the middle, that is also very important. Every molecule is going to have, it's going to have a prefix and it's going to have a suffix. So the first part is the number of carbon atoms, right? The last part is the functional group. So the last part is the functional group. What is the middle part? It could be AN or it could be EN. So the middle part tells you if it's got any double bonds. It tells you whether it's saturated. Saturated means that all bonds are single bonds. The carbon-carbon bonds are single bonds, like an alkane. So it's going to be AN. Unsaturated would mean that it would be EN. Okay, so if it's unsaturated, so then it's EN. So if there was a double bond between the carbon atoms, it would have been EN. So this is butanone. Now, if the functional group position is different, you're going to code the position of the functional group, where exactly it is. For aldehydes, you don't have to code the position of the functional group because the aldehyde functional group is always at the end. Ketones can be anywhere in the middle, so you have to tell them where exactly is the functional group. I said then you've got more than what if you have more than one functional group? Now, when you have more than one functional group, make sure that so when you have more than one functional group, make sure that you know what the precedence order is. Carboxylic acid has the highest precedence. So if a molecule is a carboxylic acid, it also has an alcohol, an amine, an aldehyde, or ketone. It's got, let's say it's got all of these functional groups. The molecule or the suffix is going to be decided by the highest precedence group. So for example, if you have this molecule over here in front of you, this one, you would notice that it's got a aldehyde, it's got an alkene, it's got a chlorine, it's got an OH as well. So who's the highest functional precedence functional group? Alcohol is over here. And aldehyde is right over here. So aldehyde has the highest precedence. So which is why the suffix of this molecule is going to be, it's going to be called an aldehyde. Is that clear? Like it's going to end with aldehyde. See,
Yes, sir. Got it.
So it's going to be an aldehyde. Number of carbon atoms, that's 4, so that's but, but it's unsaturated. That means it's got a double bond over here. So it's instead of AN, it's EN. It would have been butanol, but now it's butanol. It's AN. It's not. It's got a double bond in the middle. All the countings, the smallest position is given to the highest presence group. So which is why the aldehyde has the highest. It's got the highest precedence. So which is why it's also going to be given position number 1 or the smallest position. You're going to count everything from this side. So it's 1, the double bond is on number 2, right? So it's EN, and in front of it, you write the position of the double bond, which is 2. Every other thing is now a branch. You got 2 branches. You got an OH branch, you got a Cl branch. So if an alcohol is a branch, it's called a hydroxy branch. If a chlorine is a branch, it's always a branch. You call it a chloro branch. So you got a chloro and you got a hydroxy. So the branches are written in front of it. So this one is 3. On the third one, there's a chloro, and on the fourth one, there's a hydroxy. So that's how you name molecules. And we can try another one like this one. This one has 2 alcohols. It's got a ketone as well, and it's got a carboxylic acid as well. So the molecule is going to be named carboxylic acid, right? So it's going to be oic acid. And all the counting will be done to give this the smaller number. So this is 1, this is 2, 3, 4, 5. There's no 5 actually. 4 carbon atoms, so that's but. Should have been butanoic acid. But then you will notice that it's got a ketone as well. And the ketone is, remember, always a suffix. So before oic acid, the molecule is going to have 2 suffixes. It's going to be -one as well. I mean, it would have been a butanoic acid, but the ketone, it's got a ketone group as well. So that's also a suffix. So, I mean, it always remains a suffix. So you're going to call it a butanone oic acid. And the ketone is on second numbers, position number 2. So that's butan-2-one. The hydroxy becomes, the alcohol become branches. So you got 2 hydroxy branches. So that's dihydroxy. One is on the third one, the other one is on the fourth one. So it's C4 hydroxy, right? Is that clear?
Yes, sir.
So
sir, the hydroxy is not going to be part of the name. It's just going to be but-2-one noic acid.
Yeah, I mean I mean that would be written as branches.
Okay. Okay, sir.
I mean, if I do another molecule, let's say, unless the name of the molecule depends on the alcohol. Like if I tell you to name this molecule, it's got, let's say it's got an alcohol and it's got an amine as well. So it's first thing, who's got the highest precedence, alcohol or amine?
Sir, alcohol.
Okay, so the alcohol. So it's going to be, now it's not going to be a branch. The name will be based on the alcohol, and this would be carbon number 1, carbon number 2, and carbon number 3. So that means it's prop, right?
Yes, sir.
And it's AN, right? Because there's no double bond, propanol, right? The amine will become a branch now. So amine, if it's a branch, it's called an amino branch. So this will be 2-amino. So it's going to be 2-amino and propanol. So the alcohol is always a branch unless it is the highest presence group. Is that clear?
Yes, sir.
As the next part, you've got as I said, there's just a bit more of naming. It's as if you have a branch molecule, the main chain is the longest possible carbon atom chain that has the highest precedence groups and most constituent groups, like most things on the main chain. So you want the longest possible chain with maximum things on it. So for example, you had this molecule, the biggest chain was actually this one. It's 1, 2, 3, 4, 5, 6, I think 6 carbon atoms, because it had the most things in it and it was the longest chain. So if it's 6, It's going to be hex. And the highest precedence group was an aldehyde over here. It's got an alkene as well. It's got an alcohol as well. So it's an aldehyde. Plus it's unsaturated. So it's got a double bond. So instead of AN, it's going to be EN. You're going to count from the aldehyde group. That's 1, 2, 3, 4, 5, and 6, right? So you're going to count from the aldehyde part, and so it's hex 3-enal. The rest are all branches: hydroxy, methyl, methyl, right? You got methyl on the second one, methyl on the fourth one, hydroxy on the fifth one. So it's 5-hydroxy and 2,4-dimethyl. Is that clear?
Yes, sir.
So similarly, we tried doing this one, which is, if you look at this molecule, it's I mean, this one, I think. Let's do this one. This one was done. So the longest chain, it's 1, 2, 3, 4, 5, and 6. So 6 is hex. You can remember it should have the maximum groups attached to it. So which is why I didn't go on the other side. I went to this. I mean, when I was figuring out the longest chain, I went downwards, right? So it's hex. It's got a carboxylic acid. This is number 1. So it's hex-oic acid. It's got a ketone as well, like on the fifth one. So it's a ketone as well. So it's got 2 suffixes. And there's no double bond. So it's AN. It's hexanoic acid with a ketone as well. The rest are all branches. So you got a hydroxy branch, you got a chloro branch, you got an ethyl, a branch with 2 carbon atoms. That's ethyl, right? So chloro on the third one, hydroxy on the second one, and ethyl on the fourth one. So these are all your branches. Is that clear?
Yes, sir.
Asha, then quickly, you also did, we're going to practice naming when we go on. We also did isomers. So you've got structural isomers, just a quick summary, a recap. It's there are 3 types. Like structural isomers are where you actually change the structure of the molecule. So the number of atoms are exactly the same. All you do is you change the structure. So one of them is branch isomers, where you change the carbon branches, right? You change the arrangement of the carbon chain. So you got 4 carbon atoms. You could have 4 carbon atoms in this way as well. But remember, you have to change the arrangement. You have to change the connectivity of the carbon atoms. This is not an isomer. It's just a bent version of the same thing. Okay, so imagine if I have a chain and I put the chain straight on a table, and then I sort of bend the chain. It's still the same chain, right? So unless and until you're actually rearranging the bonds and reconnecting everything, that will be an isomer. This is not an isomer. Is that clear? These two are exactly the same thing. Is this clear?
Yes, sir.
So this one is obviously connected in a completely different way, 4 carbon atoms. Then you had positional isomers, which were that you had 3 carbon atoms, you had an OH group. The OH could be on the first carbon atom, or you can just change the position. It could be on the first carbon atom. It could also be on the second carbon atom. That's a positional isomer. So you can change the position of anything in the molecule, and that will result in a different molecule, but it would be an isomer of that. And the third one is a functional group isomer. In a functional group isomer, what you can do is you can change the functional group. Like you had a carboxylic acid, and so this one is a carboxylic acid, and you can change it into an ester. So this one over here is an ester. So you can do that as well. And there are many functional groups that are isomers of each other. You've got an aldehyde, and you can change it into a ketone. Even alkanes and alkenes are isomers. Like you got a cyclic alkane, all single bonds. That's C3H6. And what you can do to it is you can turn it into an alkene. You can create a different molecule which will have exactly the same number of. So it can have the same number of carbon atoms, right? So you can turn it into an alkene. I said then, so is that clear? Three types of isomers:
Yes, sir.
chain, positional, and
Functional.
functional group. Now you've got stereoisomers. Stereoisomers, you have two types of stereoisomers. Stereoisomers, the connections are exactly the same. It's just that the orientation is different. Like your two hands, the fingers are connected in exactly the same way, except that they're kind of pointing in the wrong direction. Tiki, your two hands are mirror images of each other. So the connections are kind of the same, except that they're all pointing in different directions. So it all depends on the shape of the molecule. So you got alkenes, that's geometric isomers. For geometric isomers, you need two things. You need a So what you need is you need a double bond. That's the first thing. And so you need a double bond. Around the double bond, the rotation is restricted. Like you can't twist this double bond or the sides independently. Okay, like if I want to like twist this side, I can't do that because the double bond is kind of locked in place. So I can't sort of rotate one side independently. Is that clear?
Yes, sir.
So independent rotation of the two sides is restricted. Like if I rotate this side, the other side would definitely rotate along with it. Okay, it's not going to happen that if I rotate one side, the other side will not rotate. If there was a single bond, independent rotation is possible. If you've got a single bond, I mean these bonds over here can spin around like a fan. Okay, just like a fan spinning around. And nothing will happen to this bond. Okay, so you can imagine these things rotating around, and this side would also rotate around, but they would rotate around independently. Over here, independent rotation is not possible. So they're kind of stuck in place. They can't move around. So if you've got a double bond, the angle is 120 degrees, it's fan shaped. So if the CLs, I mean, the minimum condition is that each group attached in the double bond must be different. They got to be different. So if I've got a double bond, maybe the two CLs are pointing downwards, or maybe one side is the other way around. The CL is pointing downwards, the other CL is pointing upwards, right? This one is a cis isomer, this one is a trans isomer, where the CLs are pointing in opposite directions. Is that clear?
Yes, sir.
And you have optical isomers where we've got a chiral center, which is going to form mirror images. The chiral center is an sp3 hybridized carbon atom, which means that it's making 4 bonds. It's tetrahedral. And all 4 groups, it's going to make 4 single bonds with 4 different groups. When it does that, the molecule will have a mirrored version as well, just like your two hands. They would look exactly the same, except that they're not the same. They have different orientation. Your right hand can stick into a glove that says right hand. It can't stick into a glove that says left hand. They're non-superimposable. Optical isomers are non-superimposable versions of a molecule. So just wait a second. I'm just trying to check. Where does A2 start? It's going to start with alkene. Yep, it's going to start with alkenes. So we'll just quickly recap alkanes that you did in.
Sir, isn't alkenes part of AS?
They're part of AS, but you'll be asked about it in A2 as well.
Okay.
So we're just revising everything. Alkenes, then we'll start A2.
Okay.
Like alkenes are very similar to benzene. So quickly, alkanes. Alkanes, single bonds. All bonds are single. Tetrahedral carbon atom is making. Whenever carbon is making single bonds, that's sp3 hybridization. So they've got low melting and boiling points. They're not soluble in water, and they're very unreactive because they're non-polar, right? They only have one reaction, which is free radical substitution, where you have UV light and chlorine or bromine is added. And what happens is that any of the hydrogens over here will get substituted by Cl. Cl is going to knock them out, and it will form halogenoalkanes. And it could be more than one Cl as well, and it's a random reaction. So not only this, there'll be multiple products that are possible, right? So you can also get molecules where more than one Cl has substituted. So you could have Cl, you could have another Cl over here, you could have another Cl over here. And the Cls that get knocked out, the hydrogens that get knocked out, they eventually turn into HCl. Right? So you have this reaction, and the reaction has 3 steps. So it's a simple substitution reaction, but it's got 3 steps. It's initiation, the first one where there's a homolytic bond fission. Can you just hold on 1 second? I said, hello, can you hear me? Hello.
Yes, I hear you.
Okay. So you got Cl radicals, right? That are getting formed.
Yes, sir.
And what happens is the Cl radicals, they are very reactive because they've got unpaired electrons, which means that their outer shells are not complete. So they try to steal other atoms from this molecule. Like you got an alkane molecule, so they're going to steal the hydrogen atoms and they're going to form HCl. So the hydrogen atom, instead of sharing electrons with carbon, will end up sharing electrons with Cl, and HCl will be formed. And the the alkane will turn into a radical. It's from ethane, it will become an ethyl radical. The ethyl radical is now short of a bond, so it's going to attack a Cl2 molecule. It's going to grab a Cl, and it's going to bond with it, and a Cl radical gets formed again. So the process just repeats, but in this process, substitution happens, and the hydrogen gets substituted by Cl. So Cl radicals initially come in, steal one of the hydrogens, they form HCl. The carbon is now short of a bond, and next is it then steals one of the Cl from the Cl2 molecule, and Cl radicals. So it's a chain reaction. Cl radicals continue to get formed. Termination step is that any of the radicals could in between just join up with themselves, because radicals are molecules or atoms that are short of bonds. So if they're short of bonds, why don't they just bond with each other? So in between propagation, they might just decide to bond with each other, right? So this carbon needs a 4th bond, this carbon needs a 4th bond, so they'll connect together and they would end up forming a molecule. This one bonds with Cl, so they end up forming a molecule. So anyways, so you got that's your termination step, and that's free radical substitution, right? Is that clear?
Yes, sir.
So anyways, let's move to alkenes now. This is where A2 organic will start. So alkenes are that you have an sp2 hybridized carbon atom. What is an sp2 hybridized carbon atom? That when an alkene is formed where you have a double bond, carbon is actually bonded to just 3 atoms. Carbon, remember, has 4 electrons. So 1 electron of carbon is bonded to one atom, 1 electron is bonded to another atom, 1 electron is bonded to another atom. And the fourth electron, that's not doing anything. That's an unchanged p orbital, which is not attracted to any atom. So it's not doing anything at the moment, right? Is that clear? That's sp2 hybridization.
Yes, sir.
So it's bonded to 3 atoms, 3 electrons. They turn into sp2 hybrid orbitals because they get stretched, or the electron cloud or the electron density gets pulled towards the atom. So this is what ethene looks like. That carbon's 1 electron gets pulled by hydrogen, carbon's 1 electron gets pulled by hydrogen, carbon's 1 electron gets pulled by carbon on the right side. So that's fan shaped, right? It's so 3 electrons are busy bonding, overlapping with other atoms, getting attracted to other atoms. 1 electron is not doing anything, right? That's over here. The other carbon is exactly the same. What do the unchanged p orbital, the ones that are not involved in bonding, what do they end up doing? They end up overlapping with each other, right? And they end up forming a pi electron cloud. So the unchanged or the unused electron, they just start overlapping above and below, and that's your pi bond. Is that clear?
Yes, sir.
So that's your pi bond, and the pi bond is a very high charge density electron cloud. There's a lot of negative charge over here, because there's a lot of strong overlapping that's happening. So alkenes have all these reactions, which are known as electrophilic addition reactions. What happens is that alkenes have a very high charge density. This double bond, this pi electron cloud, is really high charge density, very concentrated electrons over here. So what they do is that if a bromine molecule comes in, they will polarize the bromine molecule. What they'll do is they will repel the electrons in the bromine bond, and the electrons will get pushed away. This bromine will become negatively charged. This bromine will become positively charged, right? So there's going to be, it's a high charge density pi electron cloud, and it has high polarizing power. So it's going to do that. The bromine will turn into a positive ion. One of the bromines will turn into a negative ion. The positive bromine will get attracted to this high charge density electron cloud. Is that clear?
Yes, sir.
And what this positive bromine does is that it attracts all the high charge density pi electron cloud, and it eventually ends up bonding with it. So the electron cloud is gone because who stole the electron cloud? A positive bromine. So the electron cloud, which was previously over here, got attracted to bromine over here, right? And when it got attracted to this bromine, so it got attracted to this bromine. Next step is this carbon became electron deficient because this bromine over here pulled the electron cloud away from this carbon atom. It stole all the electrons and attracted all the electrons towards itself. So this carbon over here, the other carbon, became electron deficient, and then the Br minus one, which was pushed away, would get attracted to it, and it will join with it, right? Is that clear?
Yes, sir.
So you had a lot of electrophilic addition reactions. There was bromination, which was this one, that it's used as a test for unsaturated molecules. Red brown bromine or orange bromine becomes decolorized. It happens at room temperature, absence of light. So similarly, you have hydration where water gets added. In the same way, it's the same hydration reaction. 300 centigrade is the temperature. 60 atmosphere phosphoric acid is used as a catalyst, and the H and the OH gets added to the double bond in a similar way, which is electrophilic. So this one is also electrophilic addition, right? So it's going to have as a so it's going to have the same exact mechanism. There was a thing called Markovnikov's rule, which was that when you have an unsymmetric alkene, which means that you've got a double bond and the double bond is unsymmetric. Like it's the left and right side are not exactly the same. So you had the Markovnikov's rule where you had a major product and you had a minor product, which meant that the rule was that the major product H likes to bond with the carbon that is already bonded to more H atoms, right? That was the rule, that the H atom likes to bond with the carbon which is already bonded to more H atoms. So this carbon was bonded to two H atoms, while this carbon was directly bonded to just one hydrogen atom. So the major product is that the H will bond with this carbon atom, and it does not like to bond with the other carbon atom. Is that clear?
Yes, sir.
So that's a Markovnikov's rule. So and there was a reason for that. The reason was that primary carbocations are kind of unstable, and secondary and tertiary carbocations are stable. The reason behind that was that, as I added bromine over here. Just one second, let me correct this. So the reason behind this was, I'll explain the reason that when you have an unsymmetric alkene and there is electrophilic addition, water was getting added, right? Let's say HBr gets added. So H has a slight positive charge and Br has a slight negative. I mean, they have a negative charge already. So what does the double bond do? The double bond is going to repel these electrons, right? So eventually what will happen is that the HBr will turn into H plus 1 and Br minus 1, right? So the Br minus 1 gets knocked out. Is that clear?
Yes, sir.
Or in this case there was water, so the water will turn into H plus 1 and OH ions. The OH of water will get so the OH of water will get pushed aside. So you got this H plus 1. This H plus 1 is interested in the electrons over here. So it's going to be interested in one of the bond electrons pi electron cloud, right? So it's going to pull the electrons and it will eventually try and bond with these electrons, right? So that's what the H will try to do. So the H can form two types of carbocations. It can either pull the electrons from the double bond and bond with this carbon atom, and this carbon becomes positively charged, or vice versa. What it can also, let's ignore the OH, or what vice versa, what it can also do is that it will bond with the other carbon atom. And this carbon atom
But sir, doesn't H always binds with the carbon with the most number of hydrogens?
and that's a major product, right? The first one, right?
Yes, sir.
So that means it, like 9 out of 10 times it's going to do that, 1 out of 10 times it's going to do that, right? I'm just talking about the reasons why this will happen. The reason is that this is a secondary carbocation because it's got carbon chains. Like the carbon with the positive charge is like in the middle of the molecule, right? This carbon over here is at the right end of the molecule. This one is a primary carbocation, right? You can call it a 1-degree carbocation or a primary carbocation. And this one is a 2-degree carbocation or a secondary carbocation. So remember, secondary and tertiary carbocations are more stable. What's the reason for that? The reason is the more carbon chains you got, right? That means it's surrounded by, the molecule is surrounded by carbon chains, and carbon chains have electrons in them, right? So you got a carbon chain on both sides. So the carbon with the positive charge is in the middle of the molecule. So if it's surrounded by large groups on both sides, what will happen to the positive charge? The positive charge is going to be smaller, right? So imagine there's a positive charge and it's surrounded on all sides by electrons. So the positive charge will kind of get neutralized by those electrons. I mean, you've got 15 electrons over here. Sorry, carbon has 6 plus 3 hydrogens. So that's nine electrons on this side. You got 9 electrons on the other side as well. So, and there's 1 electron on this side. So that's a total of 10 electrons surrounding it. So the positive charge that's right in the middle will to an extent get neutralized and it will be smaller in size. Is that clear, Asina?
Yes, sir. Sir, could you please help me maybe like repeat this part again, like once again?
Yeah, I'm just saying, do you get the point that there's a 2-degree carbocation and there's a 1-degree carbocation that's formed?
Yeah. Yes, sir.
Right? I mean, the H could bond with the carbon on the right side. I mean, it's more likely to bond with the carbon on this on this one rather than this one, right? That's also clear, right? I mean, there are two.
Yes, sir.
So, and this is going to be a major problem because the H likes to bond with the carbon that's bonded to more H atoms, right? I'm just explaining the reason why this is going to happen. The reason is that a 2-degree carbocation, do you understand 2-degree carbocation? The one that has, you got a positive carbon, it's bonded to 2 carbon chains, right? That's a 2-degree carbocation. This one is a 1-degree carbocation because the carbon with the positive charge has only 1 carbon chain on one side. Is that clear?
Yes, sir.
So the question is, why is this stable? The reason it's stable is that the positive charge is going to be smaller in this case. Over here, the positive charge is going to be much, much bigger in size. They're not exactly the same positive charge. Because imagine if the positive carbon is right in the middle of the chain, right? So it's got a large group over here, and it's got a large group on the right side as well, with lots of electrons. So lots of electrons over here, lots of electrons over here as well. So if you've got a positive charge in the middle, the positive charge will kind of get neutralized by the electrons. I mean, so I'm sitting in the middle with the positive charge, right? There are a bunch of electrons on the right side, there are a bunch of electrons on the left side. So what will happen to the positive charge? It will get neutralized, right? Is that clear?
Yes, sir.
I mean, in total, you've got 9 electrons on this side. You've got 9 electrons on this side as well. I mean, CH3 has 9 electrons. CH3 over here has 9 electrons, right? So the point I'm trying to make is that the positive charge is smaller in size on this carbon atom. Is that point clear?
Yes, sir.
As compared to a 1-degree carbocation, if you look at a 1-degree carbocation, it's surrounded by more hydrogen atoms, right? How many electrons does the hydrogen atom has? It just has 1 electron, right?
Yes, sir.
So it's not surrounded by a lot of electrons. I mean, so most of its sides are not surrounded by electrons. So what will happen is that this positive charge is not going to get neutralized. It's going to be much bigger in size. Is that clear?
Yes, sir.
So is this point clear that one of the positive charge, like you have 2 different carbocations forming, and so you got 2 different carbocations forming. One of the carbons has a small positive charge, the other one has a bigger positive charge. This one is unstable. The reason this one is unstable is that the positive charge is so big that what it will do is it will steal electrons from this hydrogen, and it's going to take those electrons, right? Because if the positive charge is big, it's going to steal those electrons and it's going to pull those electrons back, and it will form the double bond back again. So the first step will not be able to happen. Like you had an H+1 coming in. The H+1 was the one that was stealing the electrons from the double bond, right? In the first place. This was how it would steal the electrons, right? Because it was positively charged, so it wanted electrons, so it would steal electrons from the double bond. In this way, the H became neutral and the carbon became positive. But I just told you that the positive charge is so big that it won't allow the hydrogen to steal those electrons. The positive charge that will be formed will be so big that that positive charge is going to bring those electrons back again. It's not going to let go of them. So for the alkene, it's going to be very hard to react because the carbon is not willing to let go of those electrons. Is that clear? Because it's going to get a large positive charge if it does that. Is this clear?
Yes, sir. Yes, sir.
So which is why it's very hard to form a 1 degree carbocation, because a 1 degree carbocation, it does not like to form. I mean, the carbon does not like a 1 degree carbocation. You steal the electrons from the double bond, you end up with a very big positively charged, a high charge density carbocation. That high charge density carbocation will steal those electrons back. It will not let the hydrogen take those electrons. So it's not going to form. It's very hard to form. This one would easily form. Like the hydrogen atom will come in, steal the electrons. The positive charge that will be formed over here, that's going to be very small in size. So it won't steal those electrons back. So it's more likely to get formed. Is that clear?
Yes, sir.
So just remember 2 degree carbocations are more stable, or 3 degree carbo. So the more higher the number of carbon chains. So secondary and tertiary carbocations have more electron donating alkyl chains. Charge density of the carbocation decreases, which makes for a more stable carbocation. So just remember, get this idea straight that you got a high charge density carbocation, you got a very strong positive carbon. That thing will not last. That thing is unstable. Vice versa, if you've got a very low charge density carbocation, then that thing is more likely to get formed. And how do I know it's a low charge density carbocation? Because if it's got more carbon chains around it, then that means the charge on the carbon will be kind of small. Is that clear?
Yes, sir.
Achha, so one second. So just keep this in mind, okay? Just keep this in mind. That's the reason for Markovnikov's rule. So anyways, you have alkene reactions, hydrogen halides at similar reaction, hydrogenation happened, right? That was also AS. Now I'm just going to, right at the end, I'm just going to talk about benzene a little bit. Now benzene is very similar to an alkene, right? So benzene is this thing. This is C6H6. It's got a carbon to hydrogen ratio of 1:1. Remember, in all organic molecules, pretty much all organic molecules, the carbon to hydrogen ratio is 1:2. Like if you talk about an alkane, C4H10, right? That's more than double, right? If you talk about an alkene, that's C2H4, right? That's double. So usually the carbon to hydrogen ratio is 1. It's 1:2 or more than 1:2, not 1:1. So first thing, whenever you see carbon to hydrogen ratio that's almost 1:1, the formula has a benzene in it. This is what a benzene looks like. This is a simplified structure. This is like what it actually looks like. But if you want to simplify things, think of it like this way, that it's got a cyclic carbon ring of 6 carbon atoms, and there are alternating double bonds between those carbon atoms, right? So it's like an alkene, right? With 3 double bonds. The only thing is that the double bonds kind of get mixed up, which is why you show this as a thing. That shows that the pi bonds over here, that you have a double bond, then you have another double bond, then you have another double bond. So the double bonds, they kind of start overlapping and they mix up. So here's a better picture of this. This is what benzene looks like. You can remember carbon is sp2 hybridized. There's a carbon making 3 bonds, right?
Yes,
and the 4th electron of the carbon is right now not doing anything. That's your p orbital. This one again, it's a carbon making 3 bonds, right? The blue ones are the 3 bonds, and there's a 4th electron of carbon that is initially not doing anything. Now all the carbons are sp2 hybridized. This one carbon, it's fan shaped, and then there's the fourth electron not doing anything. So what happens is that every carbon is actually sp2 hybridized, and this is what happens. They actually so what they do is they actually let me show you. Nope. So let me just show this thing clearly. There are 3 double bonds, right? So the 3 double bonds will be, let me erase that as well. So the 3 double bonds, no, got rid, just one second, get rid of this. So every carbon atom has this p orbital, right? And those p orbitals, they will overlap, and they'll form these double bonds, right? So that's your 3 double bonds, like an alkene, a pi bond, another pi bond, another pi bond, right? So that's your 3 double bonds, the way it's shown over here. Asina, is that clear?
Yes, sir.
But the thing is, if this p orbital can overlap with this p orbital over here, it can also overlap with the p orbital over here as well. Is that clear? So the thing is that eventually all the p orbitals would kind of mix up. So they won't form a double bond here, a double bond here, a double bond here. They'll kind of form a double bond everywhere. Is that clear?
Yes, sir.
So let me get back to the original. So that's my original molecule. So what happens is that all the p orbitals, they end up overlapping with each other. So that's your ring. That's your ring that's formed. So it started off as an alkene, but it's like an alkene with a lot of double bonds that have kind of mixed up with each other. Is this clear? This idea clear?
Yes, sir.
Now, the important thing is compared to an alkene, right? So this is what an alkene looks like. Now, compared to an alkene, the important idea is that when you have these pi electron clouds, the electron density is actually lower than an alkene, because in an alkene, the electrons were kind of concentrated at a particular point. Like they were overlapping, and the electron density was like maximum in the middle over here. Over here, the problem is that the electrons are kind of more distributed. It's if you look at this p orbital, it's overlapping with the carbon on the left side, but at the same time, it's also overlapping with the carbon that's on the right side. Is that clear?
Yes, sir.
So kind of both things happening at the same time. So which is why its electrons are kind of more distributed, and the charge density is kind of lower than an alkene. So what happens is that the benzene pi electron cloud electron density is more distributed, and it's got a lower charge density compared to alkenes. Is this point clear?
Yes, sir.
So just keep that in mind, and next class we'll talk about benzene now. So benzene is inherently different compared to an alkene. And they'll ask you a lot of questions about the structure of benzene. There'll be big questions on this, like 4-5 marks. So all you have to show is that, tell them that all the carbon atoms are sp2 hybridized. The angles are 120 degrees when it's sp2. They're all fan shaped. Like look at the blue bonds of carbon. They're all fan shaped, right? The pi electron cloud is above and below. So it's a completely flat molecule. I mean, this is how benzene shape molecule would look like. So it's going to be completely flat, probably like this, and I mean this one. So this one's kind of a better picture. So it's going to be completely flat like this. It's going to be completely planar. All the carbon atoms, those are your blue bonds. And then every one of them will have a p orbital. So there's going to be an overlapping cloud above and an overlapping cloud that's going to be below this. This one gives you kind of a better idea. So you see over here, it's going to be a completely flat molecule with an electron cloud where the p orbitals would overlap above and below, and they would form a ring above and below. Is that clear? So,
Yes, sir.
so this structure, you're not going to draw this. You're going to draw this structure, which is over here. But always think of this as three alternating double bonds, which are kind of like mixing up with each other. So it's a lot easier to draw this, but at the end of the day, just instead of drawing double bonds, just draw a ring around it, right? That's it. So inherently, I mean, the main question is, how is it different than an alkene? The major difference is alkenes have a much stronger electron density because the electrons are like concentrated at a particular point. Here, the electrons are more distributed. They're distributed over a much wider area. One p orbital not only overlaps on the left side, but also overlaps on the one to the right of it as well. So which is why the electron density is much, much lower. So which is why there's going to be one difference in benzene, and that is that it will have a lower polarizing power. Benzene will not be able to do this. It will not be able to do an addition reaction. Why? Because why did the bromine become polarized in the first place? Because the electron density over here was pretty high, right? So the electrons over here got repelled pretty strongly. Is that clear?
Yes, sir.
So that's the main reason. So here, let's continue in the next class then, and we'll start off with
All right, sir.
and I'll share the
Okay, sir.
I'll share the links and the PDFs as well, right?
Okay, sir. Okay, thank you, sir.
Take
See you
care.
tomorrow.
Bye bye.